So when you're looking at data, comparing two groups is pretty simple, right? But what happens when you've got three groups, or four, or even more? Let's dive into the right way, and more importantly, the wrong way, to figure it all out.
To get us started, let's borrow a great little story from statistician Andy Field. When he was a kid, he had to choose between three different types of secondary schools: the local state school, a more selective grammar school, or a private school. Three totally different groups, right? And you can imagine they might lead to very different outcomes.
So here's the big question. If we wanted to figure out which of these schools gave students a better shot at, say, higher exam scores, how would we even begin to compare them statistically? Well, the answer that first pops into your head is almost certainly a statistical trap.
Okay, so the most intuitive way to handle this is to just compare the groups two at a time. But as we're about to see, running too many tests on your data is a recipe for disaster.
You're probably thinking, hey, I know how to do this. I'll just run a few t-tests. You know, you'd compare the state school with the grammar school, then the state school with the private school, and finally, the grammar school with the private school. Boom, done. Simple, yeah?
Well, hold on a second. As these researchers point out, every time you poke and prod the same set of data, you dramatically increase your risk of making a very specific kind of mistake, what we call a type 1 error. Let's really unpack that. You see, with any single statistical test, we usually accept about a 5% chance that we're wrong, that we've found something that isn't really there, a false positive. But when you start running test after test on the same data, the chance of getting at least one false positive somewhere in that family of tests, well, it doesn't just add up, it skyrockets. This is the family-wise error rate.
Just how much does it jump? Well, with our three little school comparisons, that 5% risk suddenly blows up to over 14%. That's a huge leap in your chances of being wrong.
And oh, it gets so much worse. Imagine you had 5 groups to compare. That would mean running 10 separate t-tests. Your family-wise error rate would climb to a staggering 40%. Think about that. You'd basically be flipping a coin to see if your significant finding is real. That is just not good science. So clearly, just running a bunch of t-tests is a big no-no. What's the right way to do it? Well, say hello to a really clever tool called Analysis of Variance, or as you probably know it, ANOVA.
The way ANOVA works is actually pretty brilliant. It boils everything down to one number, the F ratio. And this ratio is basically comparing two things, the signal versus the noise. The signal is the difference between your groups, the potential effect you're looking for. And the noise is just the random, natural variation you'd expect to see within any one of those groups. So, is the signal louder than the noise? That's what the F ratio tells us.
But, and this is a big but, you have to remember that ANOVA is what's called an omnibus test. I love this analogy. Think of it like a smoke alarm. When it goes off, it tells you there's a fire somewhere in the building. A significant difference exists, but it doesn't tell you which room is on fire.
All right, so the alarm is blaring. Our ANOVA test came back significant. So what's our next move? We got to find the fire, right?
All that significant result means is that we're pretty sure the groups aren't all the same, but we still don't know how they're different. Is it school 1 versus the other 2? Are all 3 different from each other? ANOVA on its own just can't tell us.
And that is where post-hoc tests come into play. The name literally means after this, which is perfect. These are the follow-up tests, the detective work we do after the ANOVA alarm goes off, so we can finally pinpoint exactly where the differences are.
But choosing a post-hoc test isn't one size fits all. They exist on a spectrum, from what we call liberal to conservative, and it's a really important trade-off you have to make. So let's look at 2 of the big ones to really get this. On the liberal side, we've got Fisher's LSD. That stands for least significant difference. And on the conservative side, we have the Sheffey test. Now, to really understand what liberal and conservative mean here, we need a quick refresher on the 2 kinds of mistakes we're trying to avoid. First step, a type 1 error. This is your classic false positive. It's a false alarm. You shout Eureka and claim you found an effect, but really, it was just random chance. Then you've got the type 2 error. This is the opposite, a false negative. A real effect, a genuine discovery was right there in your data, but your test just wasn't powerful enough to see it. You completely missed it. Okay, so let's bring this all together. Think of Fisher's LSD as the liberal detective. This detective has more power, meaning a lower risk of missing a real discovery that's a type 2 error. But because they're chasing down every single lead, they're also more likely to raise a false alarm, a type 1 error. Then you have the Chaffee test. This is your super conservative detective. They will not make a claim without ironclad proof, so the risk of a false alarm is incredibly low. But the flip side is they might ignore a more subtle clue and miss the case entirely, giving them a higher risk of a type 2 error.
So, which detective should you hire? The one who chases every lead, or the one who demands absolute proof? Well, the answer really depends on the kind of case you're working on.
This is really the key takeaway. Think about your research. Are you in an early exploratory phase, just looking for any possible lead to follow up on later? Then, missing a potential discovery, a type 2 error, is your worst nightmare. You'd much rather chase a few dead ends than miss a breakthrough. So you go liberal. You pick Fisher's LSD. But what if you're testing something with high stakes, like a new medical drug? Here, a false positive, a type 1 error, could be catastrophic. You absolutely cannot claim it works if it doesn't. In that case, you have to be conservative. You pick the Chaffee test.
So you see, it's not about which test is magically better. The whole point is to think about the consequences of being wrong. The choice you make is all about which type of mistake is more costly for your specific project.
And that's really what I want to leave you with. Take a second and think about your own work, whatever field you're in. What's the bigger risk for you? Is it worse to claim a discovery that turns out to be nothing? Or is it worse to miss a discovery that was actually there? Your answer to that question tells you everything you need to know about which test to choose.